All right, so our first proof technique is the most basic one, which is the direct proof. Right, so here you start given an if-then statement. You start with the hypothesis, you apply the definitions of the hypothesis, and then you kind of unpack it in the hopes of you prove the conclusion, right? So this is our most basic approach here. That we'll do a couple of examples here. So I want to prove the following. All right, so I want to say for all A, B, C element of Z, if B is a multiple of A, and C excuse me, and C is a multiple of B, then C is a multiple of A. Okay, so a couple things going on here, right? So again, if-then statement, right? Direct proof means we're going to take a look at the hypothesis statement and start from there, right? Those are our hypothesis, what we assume to be true, right? And then by applying definitions, putting them together, putting those definitions together, we string together a logical argument, right? Now, the first thing we need to know is, what does it mean to be a multiple of, right? And actually, even before that, just a couple things here. We're dealing with integers, right? And in general, unless stated otherwise, we will be dealing with integers. Sometimes they'll tell us it's an even integer, it's an odd integer, right? But one thing that we can assume, right, integer is what we call a field, right? Or a vector space, which is a much, how should I say, all fields are vector spaces, but not all vector spaces are fields. If you've taken any linear algebra, then you might be familiar with a vector space, right? But here we want to get from that the fact that it's a field, right? It possesses properties that if you add two integers, the resulting is an integer. If you multiply two integers, the result is also an integer, right? So it is that's closure, right? So any element you perform the operation of addition, multiplication, right? Then it will lead to another element in that field here, or vector, in the set, we should say. Okay, all right. So with that being said here, what does it mean for something to be a multiple of another thing? So let's start by unpacking that hypothesis here, right? If B is a multiple of A, right? So to be a multiple, again, think of, let's say the values like 3, 6, 9, 12, etc., right? We could say 9 is a multiple of 3, right? 12 is a multiple of 3, right? We can write 12 as 3 times 4, right? So if B is a multiple of A, that means I can write B something like this, right? Where K is some integer, right? And the other statement would say, all right, and C is a multiple of B. So that means C can be rewritten like this, right? So J and K are integers, right? So again, properly define any new variables that were introduced, right? And again, I'm allowed to do this. I'm assumed from the hypothesis, we're told that this is true. Okay, so now let's start with our proof here. So I'll start with just our here, right? This is by assumption. All right, and now I'm gonna substitute, right? B is also written as K and A, right? So that's just substitution, right? And again, one step at a time, right? The goal is to get to showing that C is a multiple of A, which looks like I'm already here, right? What if I associate in this manner, right? That's the associative property. right? And I can also say we could let L equal to JK. Since J and K are both integers, L is a product of two integers, L is also an integer. We can write here. So what we have at the end, C is some integer L times A. In other words, C is a multiple of A. Right? Therefore, by definition, right, C is a multiple of L. All right, and sometimes you'll see this little box, a filled in box at the end of proofs. And sometimes you see QED, right? All this signifies is that we are at the end of our proof. All right, let's try one more here. All right, so here, proof that if A and C are odd integers, then AB plus BC is even. Okay. And again, right, we'll assume B is an integer. I'm told A and C are a specific type of integer, in this case, odd integer, right? So again, let's start by listing our assumptions, right? A is 2k plus 1. B is 2j plus 1, right? I want to distinguish between A and B, right? They are not necessarily the same integer. I mean, I suppose it could be, but not guaranteed. Okay, where again, K and J are Z, right? So these are our assumptions, right? And I just to be clear again, if we're defining A in a different way and B in a different way, so we have to be clear of what we are trying to say, right? So hence the definition K and J are integers. So now we have A is odd and C and B, excuse me, I had the wrong, C is odd, okay? All right, and now let's start here with here, right? This is my conclusion, is that this is even, right? Again, I want to wind up that, right? That's where I want to end. So I'll initially start by just kind of the distribution property here, and I'll write it like this, right? That's just distribution, and then I'll substitute, right? A I define as 2k plus 1. C I define 2j. So I substitute here, doing some algebra, we get 2k plus 2j plus 2. And now again, distribution, I'm going to factor out a 2. And then again, we'll let, these are all integers, right? K, J, 1, and B. So some product of integers is also an integer, so I'll let L be B times K plus J plus 1, right? And L is an element of Z, right, by the nature of the integers. So that means that AB plus BC is equal to 2L, right? In other words, AB, therefore AB plus BC is even. All right. So that concludes our proof, right? And that is our most straightforward approach, right? The direct proof. We start with our assumptions and then we take it from there.